Hello everyone, it's in July 3rd. Alright, let's get right into it. We have a tough problem today. So depending on how quickly we can solve it, we might or might not go for another one. There are n children standing in a line. Each child is assigned a rating given in the integer array ratings. You are giving candies to these children subject to the following requirement. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. Than their neighbors? What do you mean, than their neighbors? The one right next to them or the other ones? Return the minimum number of candies you need to have to distribute the candies to the children. So we have 1, 0, 2. You can allocate. So each child must have one candy. So they all have one. And this is more than this. So this is the lowest, so it must have 1. And this need to be more than that, this has 2. And this has to be more than that. But this doesn't necessarily have to be more than this, because they only need to be more than the neighbors. So we can allocate to the first, second, and third child of 2, 1, 2. That makes sense. So this is a 1. This has to be 2. And this is 2. Oh no. 1, 2, 1. The third gets 1 candy because it satisfies the above two conditions. Let's read again. With a higher rating gets more candies than their neighbors. So if I have a higher rating than the neighbors, so I only need to get more than this. I don't have to get more than that. Which means I'm gonna confirm this. So let's say we get something like this, right? So all of them will be 1, and this can be 2, and this can be 2. Oh, oopsie doozy. More candies than neighbors. So expected 9. Wait, hold on. Why is it 9? So I say all of these are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it makes sense. Okay. So what do I say? I say the child with the lowest candy will have 1. Can we just start from there? If the lowest candy has 1, I know it starts to go in. So we get all the minimum, right? The minimum will have 1 because we want the minimum number of candies. So the children with the lowest rating gets 1 candy. And then we look to its neighbors. And the neighbors must have more than 1 because the neighbors will be higher. So they will have 2. And from there, I kind of expand. So what would you do? I would. What's the length? 10 to the 10 to the 10, 10 to the 4th. So we can get those are like the starting point, right? Those are like the starting point with the minimum, with the indices, and then they connect it to 2 nodes, and then from each of them we try to traverse, right? We try to traverse. We go to the neighbors, and then from the neighbors we keep going. Okay, so we go left or we go right. And because we need to satisfy, so we go that until what? Now, the thing is, if your neighbor if your neighbor is higher than you, because we start from the lowest. So if the neighbor is higher than you, then they are deterministic. You have to go higher, okay? And if you get to a neighbor that's lower than you, that is not deterministic because you don't know, right? Because what we are doing is we're assigning the lowest possible value to each position. So we can go assign until we reach something that is the same. Reach something that has the same value, right? The same rating or lower. If it's the same or lower rating, then we don't know what to assign. At least from this branch, you don't know. So we can do that. Basically, starting from 1, we just go left and go right and try to see how far we can go. And from each minimum value, we go that. Right? So from each value, we go left, go left, go left, go left to see how much further left we can go. And then we go right, we see how much right we can go. Okay, so we've done that. We do the next one, and we do the next one. All right, and then once we do this expanding, we will end up at a position where we don't know how to go. So we collect those, and we say, okay, how can I go from here? Well, it is possible that from a different branch, we can reach here. It is possible. And from a different branch, we might be able to reach here. Well, if we cannot reach, right? So what does it mean if we have some value we just don't know? Well, it just means we have some value that's smaller than its neighbor. So if a value that's smaller or equal to its neighbor, those are uncertain. And if they're uncertain, that simply means they can take whatever value they can because they are smaller than the neighbor, so it doesn't matter. So they can just be assigned 1. I'm going to use this and try to see if it makes any sense. It is possible that doesn't make any sense. If it does not, then we use a test case to kind of see how it goes. Okay, so here it is. All right, so what do we do? Well, what we need to do is find the indices for find the indices. I mean, maybe what we can do is just list all the indices, and then we go through. If we can remove, we remove from it. We can remove from it, and at the end, we have whatever remaining, and then we just say, okay, we take them all as 1. Right? And we say, for I are in enumerate ratings, and we should say, what should we say? Indices, right? We'll say defaulted. It's called a set. And we say indices are.add I, right? And then once we're done, we say min r equals min indices, okay? And then we can say the candies. I thought it because it's 0. Well, it's actually fine. It's 1 times len ratings. Okay, and then when I go for there, if I eat every single one, I start expanding. Okay, we just say for I in indices min r, min rating, right? So for each one we extend left and right, and then we say go left. For j in range I minus 1 all the way to 0. If and then we just slowly go up, right? So if what? Ratings j, if ratings j is larger than ratings I, I will change, right? Because we going just left. So it's actually, no, it's not I, it should be j plus 1. Right, because j is from this all the way to, so if j is larger than j plus 1, which is I, if this is true, then we say candies j equals candies j plus 1, right? And we have visited it, and then we say indices ratings j, because we are at j, right? So indices ratings j dot remove j. We can remove the j, that index inside the indices, because we visited it, right? So we just keep going, and then once it's done, we go j move forward, and we try it again, until we hit this position where we don't know, and then we just break, don't consider it. So like in this one, j is smaller or equal to j plus 1, and that's the end. Okay, so that's going left. Now at the same time, we can go right. Right, we can go right. So for k in range, well, I plus 1 all the way to len ratings. Right, we'll go all the way to the end, and then we say if ratings, now we're going to say k is larger than ratings k minus 1, which is start with I. If that's true, then candies k shall equal to candies k minus 1 plus 1, and indices ratings k dot remove k, else then break. So we'll go left and right. Once we're done, we'll go to the next one, left and right. Next one. Once we're done, we just return some candies. No, that's not right. We break there. No, that's not right. So that's the first level, all right? And then, because we are removing everything inside candies. Now removing everything inside candies. Then what? Then our indices gets smaller. Or shouldn't we start from we can. We should find the smallest in the remaining. And then we find the smallest. So like we handle the initial stage, right? But we have all the others we haven't considered yet. We just considered this. So we can look for the next smallest, and it's starting from there, going out. Okay, so next smallest, from there we go left and go right, and yes, that might actually work. And then in that case, I actually might just call, we can create a, because I want to find the smallest every single time, right? So what we can do is we can say use a heap, because I want to get the heap out. So what we can do, so candies is fine, and we're not going to do this. We're going to say min heap, right? Min heap will equal to list indices dot, I don't know, indices dot what? Keys. All right, and then we say heap q dot heap phi min heap, and then while min heap, and we say min r equals min heap dot pop, no, heap pop, heap q dot heap pop min heap, and then right from this one we go left and go right, and we basically just say, which is fine. We also need to remove. Okay, we can put it here, right? We can put it here. After we're done, we can say del indices min r. Just remove it, so it won't affect anymore. All right, and then it will go. The next min heap will come out. The next one will come out. The next one will come out. And if it's not in there, it's just going to be removed. And at the end, we can return some candies. Okay? So basically, keep getting the smallest, because when the smallest, we can do a deterministic check. Okay, so we have this. Result is, now these are pretty trivial test cases. It didn't give us a good one. Well, I produce 1, 0, 0, 0, 0. How many zeros? I have 5 zeros. 1, 2, 3, 4, 5, and 2. This one will give us 9. Okay. What if I have only 1? That's the 1. Right? Okay, what do we have here? I have ratings. Okay, and then this one is candy. Ratings. I run this. We have error. Import heap q. There's no heap. Okay, makes sense. Let's try this. Try it. Runtime error. I have a key error. Okay. I don't know how much this is. 1, 2, 3, 4, 5, 6. I think it's 7. But I have a key error. That means it's already removed. No, do we even need to remove this? I don't think so. I don't think we need to remove. Yeah, I don't really think we need to remove. It's not reducing the number of computation. The computer comes from here. We have to go through them anyway. So let's redo this. I have high hope that this will be correct, because based on the result previously, this seems to be not too difficult a problem. And oh wow, what is this? I got a wrong answer. Wow, I did it worse than last time. Hold on boys. Let's double check. Expected 13. What the hell happened here? I have, should be 1, 2, 3, 4. That's 10. 11, 12, 13. It should be 13. How come I only got 12? Interesting. I think I did it. Let's just take a look. Again, let's take a look at the candies. Ooh, how is this one got reduced to? If this is larger than this, and candies j is smaller or equal to candies j plus 1. Only when this happens, then, ooh, yeah, hold on, what are you trying to say? We're trying to say is if the current j is smaller than that, then I need to add. But if the current j is already bigger, then I don't have to do plus 1, because when you do plus 1, it actually can get a smaller. Okay, so we need to add this to here as well, and this one will be current k. All right, it's smaller than k minus 1. Yep. Okay, that was oversight. Basically just means if it's already bigger, then we don't make more changes. Please be right. Come on. Let's do this. Let's do this. Okay, so this one's passed. This is not a difficult one. This is a medium. Which also means we are probably going to do another one today. And we need to check my other solutions. Of course, also check on how much test cases we have. So this will be all. Everyone go out as much as they can. I'll count that as ON, right? Because as this will expand as much as we can go, right? And then we'll go to the next smallest one, and they can expand as well. Oh, maybe we can make it faster. Hold on. Now I see the purpose of removing, because if this one has been considered before, yeah, if one has been considered before, then I don't have to consider it again. You know what? I think so. Let's try it. So we do this, and then we do the removal. Basically just say if j has been considered, then we say indices, right? Ratings j, then remove So the ideal is I will remove all the things that we have seen already. Okay, so this will be k, and I don't need to do this, and I will run, and I have error, key error. Now I have key error. So if this and j is in indices, right? If it's in it, what if it's not in it? So if it's in, that means it has not been considered before, so I need to consider it. But if it has been considered before, then I can save on the time. So k in k. Oh, that's K, my bad. Yep, I can make it faster. That will be ON because everyone is only visited once. So let's try this. I can actually write it. So we always start from the person, the kid, with the lowest rating and go into his, her, left and right. This guarantees that the candies assigned are deterministic. We use a min heap, to pop up minimum rating, and we make sure each index in ratings array is visited only once. So that's actually O1 login, because we have this one, O1 login. I believe this one will be faster once we use this little trick. Yeah. All right, let's try this. Hopefully I can get down to, oh, Lord, it's not right. Oh, it's a bloodbath. It's a bloodbath. Expected 18. Oh my, oh my, oh my. Okay, let's print out candies. Hold on a second. Okay, let's see what went wrong. So I start from 1, 2, 3, then we're done. So all of these are deleted, right? And then from here, 1, 2, 3, and 4. Oh, and then they all deleted. But then this one's deleted, so this one was not visited again. Oh my, you have to visit again. You cannot visit only once. You cannot visit everything only once. I was wrong. You simply cannot visit them only once. No way. Like this, you have to visit twice. Yeah, you know what? Screw this. Then what's the point of having all these indices, right? Well, the point is when we get it out, I can go through all the indices. So we still need indices, okay? We still need indices, but we don't need to pop it. And we can use a list. Yeah, I'm not gonna do anything weird about it. I'm just gonna be appended it, which is fine. And this is fine. This is fine. We need a heap file. This is fine. This is fine. And we have to say, we did this earlier. If candies, right? Candies j is smaller or equal to candies j plus 1. Then we need to make some change. We don't need to do this. Here is the same. So candies k, if it's smaller or equal to candies k plus 1, k minus 1, my bad. And we don't have to do this. Do we need to remove? Actually, honestly, we don't need to remove it, because once we pop, this one will not show up again. And then we pass. So what's the runtime on this one then? Yeah, so we use a main heap to pop up a main rating and update, right? And update the left and right neighbors of the current min rating. I'm not sure because this is log n. This is log n, is on log n, and each of them, well, oh, they will only visit once because if I visited already and then they already form a good, like it's already formed, and then this one will not be satisfied and that will break out. So yeah, this is still O and log n. It's still O and log n. Okay, so that's my final answer. Pretty bloodbath out there. Well, it doesn't really improve too much. Actually, it actually gets a little worse, but I just keep this, which is totally fine. All right, let's go take a look at the previous 48 test cases. Now I have 48 test cases. So it's the same number of test cases, but it was so much faster last time. Oh, 2-pass solution. What is this one? I have a helper. Interesting. Okay, so I listed out all possible conditions, which is different from what I'm doing right now. But this is on. This is on log n. That's how I've become more complicated because I have on log n. Because every time I go for the main heap added a log n to it. I see. I mean, I could have sorted it, right? But apparently you can do this without. Okay, let's see. What's the one without? And then right to left. So we go left to right. If it's larger than, then we increase. And then we'll go right to left. Oh, you gotta be kidding me. That easy? That easy? Seriously? Okay, I'm gonna write it, and as I'm writing it, I will think about it. We go, well, because if it's we have to, right? If my current rating is larger than my left neighbor, then I have to be one more, right? We have to be more. That's guaranteed. And then we satisfy the left, and then we satisfy the right. Oh, this actually makes perfect sense. Oh my god, this is from the official solution. Go left to right to satisfy the requirements, right? Requirements of left neighbors. neighbors, and then go right to left to satisfy the requirements of right neighbors. Okay, so we have candies equals 1 times, let's get n equals line ratings, right? Times n. And then we just say for I in range, that's true, 1 to n, we say if, oh, candy spelled wrong, if ratings I is larger than ratings I minus 1, then candies I will equal to candies I minus 1 plus 1, right? So once this is done, we go for j in range n minus 1 minus 1. Actually n minus 2 minus 1 minus 1, right? So we'll go right to left. Same thing, we say if ratings j is larger than ratings, say j plus 1, and ratings, no, and candies, j is smaller or equal to candies, j plus 1. Now, if it's already set up, we don't have to set up again. Otherwise, we need to set up. So j shall equal to candies, j plus 1, plus 1. That's my current understanding. And then I'm going to return some candies. Let's see if this one makes any sense. So we change this to 2, run it, pass everything. So throw this, yeah, this is ON. It will be faster. Ooh. All right, so here's what we can do. Put it here, run it. I feel like they have changed the test cases because it's still slower than we are used to have, which is fine. Doesn't really matter too much. Okay, so it solved it pretty fast. Let's try another one. Oh, I haven't. Oh my God, I have to look for it. Okay, I'm gonna try this one. Maximum consecutive floors without special floors. Consecutive floors without special floors. Alice managed a company that has rented some floors of a building as office space, has decided some of these floors should be special floors used for relaxation only. Given 2 integers, bottom and top, denote that Alice has rented all the floors from bottom to top inclusive. You're also given an integer array special, where special I denotes a special floor that Alice has designated for relaxation. Then the maximum number of consecutive floors without a special floor. So we want to return the maximum numbers between bottom and top. Maximum number of without. So basically the specials split this bottom to top into pieces, and then we want to find out is the maximum value of that. So what we can do is go create an array, and do the difference between the array, and that's about it, which I think will be oh, the special is not sorted. Okay, I'll have to sort it first. So this is 4. Which is not totally fine. Doesn't really matter. All right. So we special need to be sorted. Okay. And then 10 to the 5th. We can do sorted. We can say special dot append top, right? We don't add up front because that will make it a bit slower. So what we can do is for let's say I in range 1 to len special, right? And then what we do is special I minus special I minus 1 and minus 1, because we want a number of floors in between. So if it's 5 and 6, that's actually 0, right? And then we'll find a minimum of that. Okay, so rest will be this, and then we'll return minimum of rest and special 0, right, minus bottom minus 1. Okay, so that is our solution. We run the test case. We have this. That should be 3, and that should be 0. Okay. So we have bottom, top, special. We have max consecutives. Run it. What the heck? This is not what I had expected. Oopsie doozy. Oh, then we do minus 1. Oh, really? Oh, unless it's... Hold on. So, we don't know. Oh, those are the specials, right? So, let's not put it in. We take the special out. And, yeah, if it's a special, so those are special, that should be minus 1, right? But we don't put a top in here. So we can do this. Because the top and bottom, we're not sure, right? But the special is included. And if it's 1 and 3, I have 1, 2, just 3 minus 1, yes. So it should be top minus special minus 1, something like that. Okay, so we passed one, we failed this one. That is interesting. How? Special minus 1 shall be 6, right? Top is 9. 9 minus 6 should be 3. Or minimum. My lord, you're supposed to do maximum. Right? We're supposed to do maximum. Yeah, why did you do minimum? I don't know. Okay, always run it here just for safety. And let's submit. Oh, what the heck? Got it wrong. Wow, that's 5-minute penalty. Too confident. What? Isn't that right? Expected 13. Can we give 11? How? How is it? So 12 and 1, that's 11. 50 and 48. Don't tell me I made a mistake there. That I'll be very sorry. No. Oh my lord. This is not forgivable. It was just I don't know. Sometimes these type of thing happens. And what's the oh, you gotta be kidding me. What? Oh man. Oh man. Holy guacamole. What happened to you, man? You're supposed to be able to know this. What's the answer to this? Well, it should be 38 minus 6. Should be 20 what? Oh, 32. Ah, Lord. See, that is why sometimes it's, just to avoid this type of thing from happening. Right? It's just to avoid, oh my God. Right? It's just safer. And safer, it's more readable and less surprises. Like seriously, I mean, the runtime is the same. It doesn't really make it look any better, but it handles these edge cases better than this. Wow, this is. You know what? It's how should I put it? So not a difficult problem, but I got too cocky and overlooked quite a few details. So we'll call it O and login because we have the sort. And I don't think we can do it without sorting, right? Okay, that's probably the standard solution. Sentinels, sort. Yeah. Okay, that'll be it. All right, that'll be it for today. I will see you guys tomorrow. Adios.